I'm very grateful to be here in this conference, and yeah, so today I'm going to talk about some ongoing work with Subramanya who's here in the audience, Veronica, a PhD student in Leipzig, and Yasin, who was earlier a postdoc in Leipzig, now he's in Caltech. So it's a massive amplitudes in n is equal to 4 super Young mills, that's like Coulomb branch of super Young mills, and how it is related to the symplectic Grassmannian. Okay. So to begin with, I would say that the amplitude for the massless n is equal to 4 super Young mills can be written as integrals over the Grassmannians k comma n, okay? K planes in n-dimensional space. So we got to see a little bit of it in the lectures by Melissa in the morning. And so we have this complicated looking integral, but it evaluates into the amplitudes, 3.4 point whatever. N will be the number of external particles and k will be in which helicity sector you are in, okay? Where lambdas are like this square spinners and these are like angle spinners, and c are these Grassmannian space, k planes in n dimension. So what happens is that if you have massive particles rather than massless particles, then massive particles don't have a fixed chirality. So that means if you run fast enough, you can see the particle rotating in a different direction. So that means all the different n to the k MHV sectors will mix together, okay? And this is what can be called as a unification in the IR. That means that if you are very high in the energy, you will see different helicity sectors, but if you are in the low energy setup where you cannot neglect the masses of the particles, so you will have actually just a collection of all of them. And the massive amplitude of n is equal to 4 super Young mill are expected to have an underlying symplectic Grassmannian, which is going to unify in a way different grk comma n sectors, okay? But very little is known about these, and we don't know how to write such integrals for SPGR. So we have done whatever little bit we could do, and that's what I'm going to talk about today, okay? So a little bit of review about massive particles and n is equal to 4 super Young mill. So the external kinematic space is the momenta, external momenta and their masses, and we can use the spinor helicity formalism and write pi as this, okay? Where these capital Ij, wherever you see, these are massive spinor helicity variable, massive spinor helicity indices, okay? These are SL2 indices. And the amplitudes are written in terms of such a W. This is a supermultiplet which encompasses all the different 16 components of the supersymmetry, okay? So when you see an amplitude finally written like this, you can ask what's the amplitude for 4 W bosons. And we would have to take derivative with respect to 4 of the etas and then set the rest of them to 0 to get that particular amplitude. So this is a generating function for all of the different component amplitude, okay? And the way this is written, it makes the supersymmetric invariance manifest. And in the super Young mills, what you have are the scalars are in the adjoint representation. And because of that, the masses are Vi minus Vj. So that leads to a mass conservation. That means that M1 plus M2 will be M3, something like that. We can analytically continue such that sum of the masses are 0. Okay, so this is equivalent to saying that masses are the momenta in the compact direction. Okay, so this is just a momentum conservation in a one higher dimension. Okay. So now I'll focus mostly on the 3 particle amplitude, and for this particular setup, the 3 particle have a special kinematic. So what that refer to is that the external kinematics is not actually independent. So if you're familiar with the massless case, what happens is that either all the square brackets are 0 or all angle brackets are 0. So this is the equivalent thing here. So what you have is that this particular combination is 0. This is just momentum conservation and on-shell conditions. So 2p1.p2 plus 2m1m2 will be 0. And in terms of these angles in square bracket, we can write this as a particular matrix which determinant turns out to be 0. So that means it's a rank 1 matrix, and we can write it as a product of a column and a row vector. Okay. So these are what the u variables are. And then one can show that somehow what so happens is that there is an angle u and there is a square u, so that such a condition holds. I'll just write it here because I might use it later. Okay. And the 3 particle amplitude in this particular setup eventually turns out to be this. You can imagine that this contains all the particular amplitudes. So for instance, WWW boson's amplitude is actually contained in particular in this expression. And it's, yeah. So this should reduce to the MHV or anti-MHV massless 3-particle amplitude, okay? So if you remember the black and white dots from morning, so this should represent a gray dot, which in the massless case will become either a black dot or a white dot, okay? So now what we have is a geometric origin of this special kinematics. And the way we see it is this, that let's say that we write the spinor helicity variables in this way, where we are now seeing them as the row rather than focusing on the columns, okay? And so now these lambdas satisfy these particular conditions because of the mass conservation, okay, where omega is just it's like a one form. And so these form the symplectic Grassmannian space, where a symplectic Grassmannian is just a Grassmannian with such a condition satisfied, all right? So owing to the momentum conservation, lambda and lambda tilde have an intersection, and that intersection results into the 3-body special kinematics, okay? So one way, or one rather simple way to see that is like this. So consider these 2 cross 3 matrices, okay? And so this is a 2-plane in 3-dimensional space, this is a 2-plane in 3-dimensional space, and they do have an intersection space. And the intersection space is precisely the U variables that I showed in the last slide here, okay? So here this is a bit misleading because eventually lambda and lambda tilde are some 6-dimensional spaces, 3 plus 3, because it's a bit more complicated setup than that. So this amplitude that I just flashed earlier, this in terms of this symplectic Grassmannian can just be written like this. So delta 6 of C omega eta, where C now we're writing like this, where you can see that the upper 2 rows are the angle bracket lambda tilde, and the lower 2s are actually square brackets because of this condition that I wrote, okay? So angle UII is actually just square UII. So that means these U's are precisely the intersection space, okay? And we have amplitude written in a neat way. So in fact, we can also write the amplitude as a cyclic invariant integral over this SPGR 3,6, and that looks like this, okay? So this is now what the gray dot will be as an actual integral over the Grassmannian space. So the C is now a space of SPGR 3,6, and this condition is the symplectic condition that C should be symplectically orthogonal to itself. This says that C should be symplectically orthogonal to the lambda and lambda tilde as well. So we get momentum conservation, we get mass conservation, we get supersymmetry conservation, and we get all the factors correct as well, and we get the amplitude written in this way for this particular C. And these things are particular maximal minors of the C appearing in a particular little group frame. All right, yeah. So I'm avoiding the details here, but I'm very happy to talk about it after. Okay. And now in the massless case, so the massive 3-point amplitude written unifies both the MHV and anti-MHV 3-point amplitude. And in the massless case, we can see that the C written in this way becomes this. So there are 2 particular solutions that can appear. It can either take this form, which is the anti-MHV, which is the black dot, or it can become this, which is the MHV case. Okay, so the SPGR 3,6 becomes GR 1,3 or 2,3. So the unification in the IR that I showed in the first slide, we can see at least for the 3-point amplitude. Okay, and the amplitude is still C omega eta. So this is the 3-particle massless amplitude, which is still this, with C being this or this. Okay, MHV or anti-MHV in this way. Okay, and well, how do we go from 3-point to higher point? We will have to glue them together using on-shell methods and so on. So that requires a detailed analysis of Playback graphs of symplectic Grassmannian, and which some of it exists in the math literature, and we will look at it in future whenever we look at it. So for instance, for 4-particle, we can actually see what is the symplectic structure. So what is the C? What is the solution of the C? So all the angle brackets and all the square brackets, we just stack on top of each other, and that's the 4x8 matrix that gives the right amplitude and everything. So that's the C. Okay. So even though I'm not showing, because we don't have very good understanding of what should be the right 4-particle integral that gives us the 4-particle amplitude, but we know what is the structure that we expect. It will still have such an integral and those delta functions. Okay, and yeah, so to effectively understand the gluings, we need to better understand the integral. Is the measure a D-log form? We don't know. And Subramanya will talk about gluings of these things on the next Thursday, but without the Grassmannian things. And yeah, and in the end, I'll just mention that the massless supermultiplet in 1,1 superYAG in 6 dimension is the same as the short multiplet massive in the n is equal to 4 superYAG for the in 4 dimension. Okay, so that means we can view the mass in the 4 dimension as a momentum in the compact direction, and we will have the similar Grassmannian structure for 1,1 theory as well. Okay, so we can still look for what is the kinematic space, and for instance, for 3-point amplitude, is there an intersection space and so on, and we still do have the same interpretation of an intersection space. So in 6 dimension, we'll have 2 kind of spin helicity variables, lambda and lambda tilde, and both of them are SPGR independently, and then both of them have an intersection space in between both, okay, amongst each other. So we get the 3-point amplitude like this. Again, I'm omitting the details here, but that's roughly the idea. So again, here, at least in this case, we don't know how to write down the actual integral, but this is roughly the geometry that it will have. So that's all that I have to say. Thanks.
Thank you for the nice talk. Questions for Amit?
Thanks a lot for a very nice talk. I remember from some, I think, bosonic works on massive 3-point amplitudes, that at 3 particles there was some subtlety that most formulas, they needed some kind of reference vector or reference spinner. And I was just curious, your formulas looked so nice, I didn't see any. So I was wondering, do you have a reference spinner? And if so, where does it appear? Or do you have an equivalent to this?
Well, there is a reference spinner Q here. Is that what you're referring to? So 3-point supersymmetric amplitude will have a reference moment. That's what you're saying. Yeah.
Yes,
So we still have a Q, but yeah, it is still there. Yeah.
So it's then expected that when you do this BCFW gluing, that eventually this Q will drop out.
Yes, exactly. Yeah, that we can see even without knowing the symplectic structures and so on. We do understand from simple BCFW constructions and so on.
Okay, thank you.
But here the idea is just this, that somehow there is a preferred plane with preferred direction, U direction, and then this Q is just anything that's not U. So U is dictated by the kinematics itself, and then you want to project out things that are not U, so you need a reference spinner. That's roughly the idea. Yeah.
Okay, I just wanted to ask, so when you take this massless limit, you don't get any other states that are not in the supersymmetric massless multiplet?
Oh, no, actually there are 16 states in the massive state, 16 states in the massless state. So you can't go out. So that's why it's a Coulomb branch. So yeah, so you stay in the same thing. Yeah.
Okay, let's thank Amit again for a great talk.